Now that universities are finally changing their curriculum to include languages like Rust instead of this garbage, I think now is a time better than any for us to wrap our heads around some of the alien-looking syntax in Rust. So today we're going to be tackling this expression, which you might have come across as the return type of some functions, especially ones which may return multiple types of errors. Specifically, it serves in coalescing multiple error types into some constraint identity. But we'll get to that later. First, let's walk through the parts that make up this data type. A result is an enumerable or an enum type with two variants, OK and err. Enum variants in Rust are mutually exclusive, meaning a function returning a result would either be a success value wrapped in an OK variant or a failure value wrapped in an error variant. Note that the OK and the error variants only tell us that whatever is wrapped inside them is a success or an error value. To tell the compiler the concrete types for these values, the result enum itself takes in two generic types, t and e, for the success and the failure values respectively. Now, since the success value depends upon a function's output, we leave it as a generic t for now, and focus on the more hairy-looking error type. When working with different data types in Rust, the primitive types like bytes, integers, or floating point numbers are all allocated on the stack in our computer's virtual memory. The sizes of these structures are fixed and known to the compiler. For composite types like vectors or strings, their sizes may depend upon user input, for example, and are thus not known to the compiler. These dynamically sized types are allocated on the heap memory. Unlike primitive types, passing them around as function arguments or return types actually translates to passing around a pointer to the memory allocated on the heap. Wrapping a value in a box type, sometimes referred to simply as boxing a value, explicitly puts it on the heap. This again means that we're passing around a pointer to the value in the heap. But why does an error have to be wrapped in a box? Doesn't the compiler already know the size of each error type? Well, yes, but the type we're specifying inside the box is not a concrete type, but more of a constraint for what can go inside the box. Differently sized structures can be put inside the box as long as they conform to this constraint. You see, a standard error is something known as a trait, which defines a set of methods that a structure must implement to qualify for that trait. Here, a structure must implement the format method to qualify as an error. This means any arbitrary underlying type can be made an error as long as it implements this method. Great, we've convinced the compiler to not care about the underlying concrete type. It can pass around a pointer to the error as long as the trait constraints are met. Except there's a teeny tiny problem. Implementations of the format method could very well differ from structure to structure. Whereas a network error might give you details about a peer address, a logging error might tell you about the file it couldn't open. Now that the compiler has forgotten the underlying type and only cares about a pointer, it has no way to deduce the correct implementation to call for the structure at hand. And this is where I kinda lied to you, because when you're passing something that implements a trait inside a box, you're not passing one pointer, you're actually passing two. The first points to a structure allocated on the heap, but the other points to a table. This table itself contains function pointers to the trait method implementations specific to our struct. These tables are known as dynamic dispatch tables since they dispatch the correct machine code that can be called on whatever object we have at hand. Speaking of objects, this structure created with the use of the dyne keyword before a name of a trait, be it a reference or a box, is known as a trait object or a fat pointer. These trait objects are inherently opaque because they're raw, untyped pointers. The underlying fields cannot be accessed directly. One can only call the methods that they expose. With all of this context, you should be able to explain this expression to yourself or a friend, but let's breeze through the ideas that we've learned so far. A result is an enum with two variants, OK to wrap success values and error to wrap, well, errors. We use a box to allocate memory for error values independent of their size as long as they implement the format method defined in the trait. These methods themselves are accessed through the dynamic dispatch table, which of course leads to the struct-specific machine code. In practice, we'll often use this expression with the question mark or the try operator. This syntax sugar boils down to a match statement like this, which consumes the success value, if it's present, or it resorts to bubbling up the error values. Finally, there's an awesome crate known as Anyhow, which banks on this idea of error trait objects. It defines its own result enum that takes a generic type t for the success value, but the errors are taken care of by the crate itself. And we get the added benefit of being able to add context to our errors. So yeah, thank you for watching this video till the end. I hope you learned something. And as always, all the sources as well as code used to render these animations will be linked in the description, and I'll see you around.